So we will continue with section 4.2 and part B. Part B involves multiple bonds. So multiple bonds form when there are not enough valence electrons to complete octets. Lone pairs of electrons are then converted into bonding pairs as needed. So as you know, a single bond is a pair of electrons, means 2 electrons, and you draw that as a single line. And those electrons are shared between the two atoms. In a double bond contains 4 electrons because 2 pairs of electrons are shared. So it looks like 2 lines parallel to each other between the 2 atoms. So each line is 2 electrons, so that's 4 electrons that are shared between the 2 oxygen in the example here. In a triple bond, we have 6 electrons that are shared. And so we draw this as 3 lines. Each line corresponds to 2 electrons. So 3 lines times 2 electrons each. It's 6 electrons shared between the 2 nitrogen in this example. So let's go through some example on how to draw the Lewis structure of C2H4, which will involve a multiple bond. So C2H4, you want to arrange the atom first. And here, C carbon is the first atom. It's more metallic than hydrogen, so you would place it in the center. And you have 2 carbons there. So both carbons will be central atom. And molecules tend to be symmetrical, so you will surround each carbon with 2 hydrogens. You will split the 4 hydrogens equally between the 2 carbons. So you would have the 2 carbons in the center, and then you give 2 hydrogens to each carbon. Next, you want to count the total number of valence electrons. So we have 2 carbons from group 4A. They bring 4 electrons each. 2 times 2, it's 8 electrons from the carbons. We have 4 hydrogens. They each bring 1 electron because hydrogen is in group 1A. 1 electrons times 4 hydrogens, that's 4 electrons from the hydrogens. And now you add that, 8 plus 4, it's 12 electrons for the structure of C2H4. So next you want to add the bonds between the atoms. So you will add bonds between the 2 carbon and then between each carbon and hydrogen that are next to each other. By placing those single bonds, we have 5 single bonds times 2 electrons each. It's 10 electrons that have been used, minus, taken out of the 12, that's 2 electrons left. So the next step is to distribute the lone pairs and give octet to atoms, starting from the outside atoms. And here we only have hydrogens as outside atoms, and hydrogen doesn't need more than 2 electrons. And so when it has a single bond, it already has 2 electrons around it. So the hydrogens, you never give them lone pairs. So they will stay like that. And so the 2 extra electrons left, you will give them to a carbon to give it an octet. On that carbon now, we have 6 electrons from the bonds plus 2, it's 8 electrons around it. And now we have no more electrons to distribute. So let's do the count here. We have 5 bonds times 2 electrons each. It's 10 electrons from the bonds, plus a lone pair, 2 electrons from that lone pair. So 10 plus 2 is 12 electrons. All valence electrons have been used. However, one of the carbons still does not have an octet. One has the octet, but the other doesn't. So we need to share then the lone pair with the other carbon so that both carbon have an octet, and we don't bring this way new valence electrons. Since we have used them all, we cannot bring any more. So starting from the structure we had earlier, you will change now one lone pair into a bonding pair, forming a double bond in this case between the two carbons. So when you share that extra lone pair, now both carbons have an octet around them. They have two single bonds plus a double bond. That's 8 valence electrons around them. And each hydrogen has a duet. And so all atoms have their octet or duet. And let's count the total number of valence electrons. So we have 4 single bonds times 2 electrons, it's 8. Plus a double bond, it's 4 electrons. So 8 plus 4 is 12. And so we do have our 12 valence electrons in total. So we know this structure is correct because the total number of valence electrons is correct and the atoms have their octet or duet. So let's go through another structure, the structure of carbon dioxide, CO2. So CO2, the first atom in the formula is carbon. So carbon will be in the center and it will be surrounded by the 2 oxygen. As always, carbon always tends to be a central atom, and molecules are symmetrical. So that's the best way to have a symmetrical molecule here. The second step is to calculate the total number of valence electrons that we can distribute. We have one carbon. Carbon from group 4A brings 4 valence electrons. So that's 4 from carbon. And we have 2 oxygens from group 6A. They bring 6 valence electrons each. 2 times 6 is 12, plus 4 is 18 valence electrons. 12 plus 4, sorry, is 16 valence electrons in total for CO2. So the next step is to do the lines that symbolize the bonds between the C and the oxygen. And so by doing this, we have used two single bonds times 2 electrons each. It's 4 electrons. So you do 16, the total, minus 4 electrons from the bonding electrons, and that's 12 electrons remaining. Place the remaining electrons using lone pairs to complete octet of outside atoms first. So that means you want to do the octet for the oxygen, not for the carbon at this time. So each oxygen at this time has only 2 electrons around them. So you want to give them 6 more by doing 3 lone pairs on each oxygen to give them octet, right? So 3 lone pairs, that's 6 electrons, plus the single bond, 2 more electrons, that's 8 electrons around each oxygen. By doing this, you have used 12 electrons, which was the number of electrons left. So at this point, we have no more electrons available, right? No more electrons available, but carbon doesn't have an octet. So we will need to bring lone pairs and share them to carbon so that it has more electrons. So to obtain an octet, the carbon atom must share lone pairs of electrons from each of the oxygens. So each of the oxygen will have to share a lone pair. And so that will create 2 double bonds on either side of carbon. And so this way, each oxygen has 4 electrons from lone pairs plus 4 electrons from the double bond, each of them. And then carbon now has 4 electrons on one side and 4 electrons on the other side. That's 8 valence electrons as well. So each atom has an octet. And now let's count that we have our 16 electrons in total. So it's 4 electrons from the lone pair on one oxygen, plus 4 in a double bond, that's 8, plus another 4 from the other double bond, that's 12, plus 4 as lone pairs on the second oxygen, that's 12 plus 4, 16. So we do have our 16 electrons in total. And each atom has an octet. So that's the Lewis structure for carbon dioxide. Let's do the Lewis structure for HCN, the hydrocyanic acid. So you want to arrange the atom first. And here, the way atoms are arranged is the same way as they appear in the formula. Carbon will be the central atom, and you have hydrogen on one side and nitrogen on the other side. Next, you want to calculate the total number of valence electrons that the structure contains. So there is 1 electron coming from the one hydrogen, 4 electrons coming from carbon because it's in group 4A, and 5 electrons coming from the nitrogen atom because it's in group 5A. So 1 plus 4 is 5, plus 5 is 10. So we have 10 electrons total for this structure. The next step is to attach the atoms with single bonds. So we will do single bonds between the C and the H and the C and the N. And now we subtract those electrons we used in the bonds from the total. So 10 electrons total minus 4 electrons used for the bonds. That's 6 electrons remaining. So now we want to place the remaining electrons using lone pairs to complete octets of outside atoms first. And you will share lone pairs to complete the central atom octet if needed. So here, hydrogen doesn't need a lone pair because hydrogen is an exception. It doesn't want an octet. It wants a duet, 2 valence electrons, and it has them when you do a single bond. So hydrogen, no need for lone pairs there. Nitrogen needs an octet, and it has only 2 electrons right now from the single bond. So we will give it those 6 electrons remaining as lone pair around nitrogen. So that's it, 6 plus 2 from the single bond, that's 8 valence electrons around nitrogen. However, now carbon is not happy. It doesn't have an octet, and there is no more electrons available. So nitrogen will have to share a lone pair with carbon. Hydrogen cannot share, it doesn't have any lone pair. So it has to come from nitrogen. And it will need to share actually 2 lone pairs because 1 lone pair would not be enough. That would be only 6 electrons around carbon. So nitrogen needs to share 2 lone pairs. So that's going to be a triple bond between C and N. And that triple bond contains 6 electrons plus 2 electrons from the single bond with hydrogen, and that makes an octet for carbon. And nitrogen still has its octet because the triple bond provides 6 electrons plus the lone pair on nitrogen. That's 8 electrons around it. So both carbon and nitrogen have their octet. Hydrogen has its duet. And let's count the total number of valence electrons. So we have 6 electrons from the triple bond, plus 2 from the lone pair on nitrogen, plus 1 from the single bond with carbon and hydrogen. So 6 plus 2 is 8, plus 2 is 10. So we have 10 electrons in total, and that's the correct number of valence electrons for the HCN structure. So that's the correct structure for HCN. So we will practice some more with those 4 molecules. and do the Lewis structure for them. So it is important that you try this on your own before you watch the answer. These Lewis structures will not be as detailed, and so if you need more help with this, then ask me during a Zoom meeting and then I can provide more help. So CS2. CS2, you will want to place the carbon in the center and surrounded by the 2 sulfur. You need to count the number of valence electrons. There is 4 from carbon plus 2 times 6 from the sulfurs, because sulfur comes from group 6A, has 6 valence electrons. So that's 12 for the 2 sulfur plus 4 from the carbon. That's 16 electrons for CS2. Then you would do the single bonds between sulfur and the carbon. That would use 4 electrons. So 16 minus 4 would be 12 electrons at that point. Out of 12 electrons, you can do 3 lone pairs on each sulfur. So each sulfur would have 3 lone pairs and a single bond with carbon. So the sulfurs would have their octet at that point, but carbon would not. So you would have to share lone pairs from the sulfurs with the carbon to give him lone electrons. And so each sulfur would have to share, and that would be 2 double bonds around the carbon to have 8 valence electrons. So carbon now has an octet. And the sulfurs, they still have 4 electrons from lone pairs plus 4 electrons from the double bond. That's 8 electrons around each sulfur. C2H4. Here you would place the 2 carbons in the center and you would give each carbon 2 hydrogens. Carbon brings 4 electrons times 2 carbon, that's 8 electrons from carbon. Hydrogen, they each bring 1 electron times 4 hydrogen, that's 4 electrons from the hydrogens. So 4 plus 4 plus 8 from the carbons. That's 12 electrons for C2H4. You would do single bonds between all the CH and the CC. And that would use 10 electrons because 5 bonds times 2 electrons each, 10 electrons. And then the 2 electrons left over, you would put them to 1 carbon, but that carbon would have to share with the other carbon. So it's a double bond between the 2 carbons so that they each have an octet. And you can see that each carbon has an octet. Each hydrogen have a duet. And we have, so let's count the number of electrons. 4 single bonds times 2 electrons, it's 8 electrons plus the double bond brings 4. 8 plus 4 is 12 electrons in total. Then H3PO4. So for this structure, what you have to know is that the phosphorus would be the central atom. Then you would surround the phosphorus by 4 oxygens, the 4 oxygens. And then you would give the hydrogens to 3 oxygens. So each hydrogen would be bonded to a different oxygen. And so you would have 3 oxygens bonded to hydrogen and 1 oxygen by itself. Let's count the total number of valence electrons. Hydrogen, there is 3 of them. They each have 1 valence electrons. So that's 3 from the hydrogens. Phosphorus in group 5A brings 5, so 3 plus 5 is 8. And oxygen, group 6A, they bring 6 valence electrons each, times 4, that's 24. So 24 plus 8 That's 32. So you would have 32 electrons in total in that structure. And so you can see here how each oxygen is bonded to P, each hydrogen is bonded to an oxygen. So all these single bonds are using, so it's 1, 2, 3, 4, 5, 6, 7 single bonds times 2 electrons, it's 14 electrons. So 14 electrons in single bonds. Then you would distribute the lone pairs, and each oxygen that is bonded to an hydrogen will need only 2 lone pairs because they already have 4 electrons around them from the 2 single bonds. So these 3 oxygens using 2 lone pairs each, that's 3 times 2, 6. 3 times 4, sorry. No, 3 times 2, 6. But 6 lone pairs times 2 electrons, it's 12 electrons. Plus the 14, that's 26 electrons. And we still have 6 to distribute, and those 6 would go to the other oxygen that has a single bond. You would give it 3 lone pairs. And this way the structure is complete. So each oxygen have an octet, and the phosphorus has its octet as well. So for P2H4, P would be in the center, and you would give an hydrogen to each P, very much like the C2H4 there. Counting the number of valence electrons, so phosphorus brings 5 each, so times 2, it's 10 electrons from phosphorus. Then 4 hydrogens, they bring 1 each, so it's 4 electrons from the hydrogen. So you have 14 electrons in that structure. So be careful, it's 2 more than the C2H4 structure. So that's why in this case, when you have done the 5 single bonds between the P and the H and between the 2 P, you have used 10 electrons, but you still have 4 electrons to distribute. So you will give a lone pair to each P, and that will use those 4 electrons, and that will give an octet to each phosphorus, because each phosphorus has 6 electrons from 3 single bonds, plus a lone pair gives 2 more. So they each have an octet. So you have 14 electrons in total. The phosphorus have their octet, and the hydrogens have their duets.